In this video, we'll be talking about how to calculate the work in an isothermal process. So here we have an example of an isothermal process. I see that I begin at this starting pressure, 0.3 liters, and I'm ending at this final volume, 0.1 liters, and we've increased our pressure by a factor of 3. Notice that as we decrease the volume by a factor of 3, we increase the pressure as a factor of 3, so that PV is equal to a constant. Remember that we also have the ideal gas law, which is an empirical observation. PV equals the number of moles, nRT. R is the gas constant, whose value is given here, and T is the temperature measured, remember, in Kelvin. Must use Kelvin. Now notice, if PV is constant and we're working with a constant number of moles, which is generally the case when we compress a cylinder of sealed gas, then temperature must also be constant. PV is constant, N is constant, so T must be a constant as well. What this means is that the energy of the gas is constant. We are not changing its temperature. So this means, remember, the change in energy for this gas can only happen from two processes. They are the heat and the work. So the total change in energy, if the temperature doesn't change, is 0. This means that the heat is equal to minus the work. We can't calculate the heat directly because there's no change in temperature, so we could not use our Q equals mc delta T relationship. But we can infer the heat if we can calculate the work. So we're calculating heat indirectly, calculating work directly. Now what is work? Remember that work is the pressure times the change in volume over the course of this procedure. And pressure here is a function of volume. We'll see how to get that from this relationship. But we need to add up all these bits of change in pressure as the volume changes. So we're going from our initial volume, V initial, to our final volume, VF. And we want to think about point of view here. This gas is being compressed. That means if we released it, we would get work out of it. So if we are decreasing the volume of the gas, that means that we are putting energy into the gas. Since this is a negative change in volume, I know that I also will need another negative sign is one way to think about this. So I want to end up with a positive work. When work is done by the gas, go in the other direction. This is like expending energy from the food that we eat, so its energy is going to decrease. So doing work on the environment, even though it's a positive thing to get work out of the gas, it's at the expense of the gas. So this is from the gas's point of view. Work is equal to minus the integral V initial to V final of PdV. All you integral fans out there know that I can reverse these bounds and disregard this minus sign. So the integral from A to B is equal to minus the integral from B to A. So let's see what this integrand looks like. I know that PV equals nRT. T is a constant here, so this tells me that P is equal to nRT over V. So I'll write that as nRT times 1 over V. Why am I doing that? Well, if these are constants, then they can commute with the integration process, so this is equal to minus nRT. Remember, N is the number of moles, T is the temperature in Kelvin, and R is this gas constant, integrated from V initial to V final of this function, 1 over V dV, or we could write it as dV over V. Now you might recognize this primitive form from your basic calculus knowledge. So the integral of 1 over x as an indefinite integral is the natural log of absolute x. So I know that this is going to be minus nRT times the natural log of volume evaluated from V initial to V final, which I know also, let's come up here where we have a bit more space. This work is equal to minus nRT times natural log of V final minus natural log of V initial. And now we can use our log laws to simplify that. So this is equal to nRT times the natural log of this ratio, V final, over V initial, since I know that the difference of logs is equal to the log of the ratio. To double check what's going on here, remember that we've compressed the gas, and that means its energy is going to increase. So we want to end up with work that is overall positive. I see I have a negative sign here. Temperature measured in Kelvin is going to be positive, and so will our number of moles. Gas constant is always positive. So this natural log needs to be a number that is less than 1, because I know the ratio needs to be a number less than 1, because I know the natural log of a number between 0 and 1 is negative. So this means Negative times negative would give me a positive. Let's check that. Is V final less than V initial? Yes, it is. So this will work out correctly, and we will end up with a positive amount of work. Now, what about the heat in this process? Well, remember, heat is equal to minus the work. So we can tell heat equals minus work equals positive nRT natural log of V final over V initial. So this has shown us how to calculate both the work and the heat in an isothermal process, which is a slow process that does not change the temperature of the gas as it's compressed.